Alright, so this is the problem we're going to be looking at today. On the face of it, it's quite a simple problem. It's a simply supported beam, two supports on each end, as you can see on the image, and an uniformly distributed load of 5 kilonewtons per meter. And the cross section of this beam is the angle, the L-shaped section. Our objective here is also quite simply stated. We want to know the deflections of this beam. We know that given this load, the beam is going to deform like this. It's going to display a deflection, and at any point here I can calculate the value of the deflection, nu. This is not a v, this is a Greek letter called nu. So if I can determine the value of this deflection, nu, at every point along the axis of our beam, we're going to have the value of nu as a function of the coordinate x. X just positions our cross-section along the length of the beam. So we're going to study this problem in two ways. First of all, we're going to solve it analytically. So we're going to begin from the differential equations that describe this problem. Then we're going to solve these equations, and we're going to find the function nu of x, the elastic curve, which is what it's called. Then we're going to simulate this same problem in ANSYS, a finite element analysis software, and then we're going to calculate the same deflection, and we're going to show that they match. At least we hope to show that they match, the analytical solution and the numerical solution. So on the face of it, this is quite a simple problem. It's kind of a beginner exercise in structural analysis and strength of materials. But what I hope to show is that there can be much more to a simple problem like this. When we look more carefully at how this structure would actually be built, we're going to see that there's a lot more complexity hidden even in such a simple problem. So I'm going to begin in an unusual fashion perhaps by recalling the relationship between this line and this cross section. So of course the real structure is three-dimensional, so it's going to be an L shape like this, and I'm going to represent this real three-dimensional structure with a line and a cross section. What is the relationship between this line and this cross section? And this is how this works. This line passes through the centroid, the center of mass of the cross section. So this real three-dimensional structure is being imagined as a bunch of thin cross sections. So you can stack an infinite number of these sections to get our three-dimensional beam. So for each of these cross sections, which has this exact shape, there is a point which is the center of mass, or the centroid of the section. So for each imaginary section, we have a point defining the centroid. If we connect all the points using a line, this is the line that we get. So that's the relationship between these two, between this line and the cross section. This might seem unimportant now, but much later on we're going to see how meaningful, how important this observation actually is. Alright, having said that, let's begin with the first approach, which is the analytical solution to this simply supported beam. Alright, so this is the fundamental equation of the elastic curve. We have the second derivative of the elastic curve is equal to the bending moment over the elastic modulus times the second moment of area. So this is the equation we need to solve to find out the value, the function actually, nu of x. This is not a v, this is a nu, the Greek letter. So since we want to find this function, we need the elastic modulus. This is given because we have the material. We need the second moment of area, which we also have because we have the cross section. And we also need the bending moment, right? So this is the only thing we do not have yet. So let's solve this beam. It's a statically determinate beam, so we can find the bending moment quite easily. So our beam is simply supported, meaning it has pin supports on both sides, and it's loaded like so, right? So this is my load, Q. This is my length, L, of the beam, and the cross section, which I'm going to call S1, is our angle section. The dimensions are 100 millimeters on the side, 10 millimeters of thickness. Alright, so first of all, let's find the bending moment, M. So M is going to be a distribution here, right? For a simply supported beam with a uniform load, we know that the maximum value of M occurs in the middle of the span, right here. But we are not interested in the maximum value. We want the function m of x. as it varies with the length. So what I'm going to do is this. I'm going to calculate first the reactions in the supports. Let's call them R1 and R2. And then I'm going to calculate the function m of x. So by symmetry here, I know that R1 is equal to R2, and both of them are equal to the load times the length of the beam divided by 2. We have that the reactions are equal to 5 kilonewtons. So now that we have the reactions, we can draw a diagram of only a fraction of the beam. So now we have the load here, the load Q, acting on the beam. And I'm going to look only at a small fraction of the beam, up to position X. So I know that here on the left I have a vertical reaction, which is 5 kilonewtons. And I also know that this Q value is also 5 kilonewtons, just per meter. So now I need to determine what is the bending moment here in this section which I have interrupted, so that the bending moment balances the loads on the left. So this fraction of the beam has to be in equilibrium. For this fraction to be in equilibrium, the loads on the left must equal the internal reactions on the section which I have cut. So on this section that I have cut, I have a bending moment and I have a shear force. I'm not interested at the moment in the shear force, so I'm just going to ignore it for now. I only want the bending moment. So to calculate this bending moment, I'm going to use this expression, which says that the sum of all moments in a given point must be equal to 0. Otherwise, your beam would be rotating, right? All moments must, when summed together, must equal 0. That's the equilibrium condition, one of the equilibrium conditions. So I'm going to choose as a point to calculate the bending moments this point which I'm going to call A. Why am I choosing A? I'm choosing A because the vertical shear force here is going to generate no bending moment on this point itself, on A. So I don't need to know what is the value of V to account for its contribution to the bending moment on point A. So the bending moment at point A, the reaction, which is 5 kilonewtons, times the distance x, so force times distance is the bending moment, minus, because it's in the other direction, the 5 kilonewton meters of the distributed load, times x, which is the length over which the load is distributed in this fraction of the beam, times the distance from the center of application of this load to the section, to the point A. The point at which the equivalent force is going to be acting is going to be in the middle of the segment. So it's going to be x over 2. And I have two more contributing factors. The value of m, the bending moment on the cross-section that I have interrupted itself, and the contribution of the shear force on this cross-section, times the distance from V to point A, which is 0. So this is why this term disappears. And all of this must be equal to 0. M, the bending moment, is going to be equal to 5 over 2 times x squared minus 5 times x. Alright, let's check to see if this expression for m of x is correct. I'm going to check at 3 points. So I know that on the left support and on the right support, the bending moment must be equal to 0. And I also know that in the middle of the span, the bending moment must have its maximum value, which we know from this particular case that the maximum value is Q times L squared over 8. So I'm going to check on that expression which I have just found if the bending moment at the left support is going to be 0, at the right support is going to be 0, and if the bending moment in the middle of the span is going to be Q times L squared over 8. So let's check it out. So first of all, left support, x is equal to 0. Well, if x is equal to 0, then m is also equal to 0. X multiplies both terms. Next, we have the right support. At the right support, we have the x equals L, which is 2. So we're going to have m equal to 5 over 2 times 2 squared minus 5 times 2. So this cancels out. Here we have 10. Here we have minus 10. So the bending moment is going to be indeed 0. And finally, in the center of the span, we have x equals L over 2, which is 1. So the bending moment is going to be 5 times 1 over 2, 1 squared, right, over 2, minus 5 times 1. So this is 5 over 2 minus 5. This is minus 2.5 kilonewton meters. Oh, sorry. Kilonewton times meters. So this is the bending moment in the middle of the span. Let's check to see if it matches the known formula. M max is equal to Q times L squared over 8, which is going to be Q is 5, L is 2, so we choose the 2, divided by 8. So we're going to have 5 times 4 divided by 8, which is 5 over 2, which is 2.5 kilonewton meters, which is exactly what we had here. So our expression seems to be correct. The bending moment as a function of the position is equal to 2.5 times the position of the cross-section squared minus 5 times the position. So now we can finally integrate this expression for the bending moment twice to obtain the value, the function of the elastic curve. The elastic curve is going to be 1 over EI integral m of x dx. I brought this fraction outside of the integrals because neither E, elastic modulus, nor the second moment of area vary along the length of the beam. They're constant, so they do not vary with x. So I can bring them outside of the integrals. Alright, so for now I'm going to forget about this guy, and I'm just going to integrate m of x, which is a polynomial. It's quite simple to integrate. So on the first integration, we're going to have 2.5 times x cubed over 3 minus 5 times x squared over 2. This is the first integration of this expression. But because we're not integrating with any limits here or here, then we're going to have constants, integration constants. As a result of integrating this expression once, we're also going to have a constant which I'm going to call C1. So after the first integration, this is my result. I still need to integrate a second time to obtain the value of the elastic curve. We're going to have 2.5 times x to the fourth power over 3 times 4 minus 5 times x to the third divided by 3 times 2. I'm also going to have C1, which was here, now being C1 times x, and because I have integrated yet again without the limits of integration, I also have to add a constant. I'm going to call C2 this time. And this is the expression for the elastic curve. So with this expression, we should be done, right? We know how the beam deflects as a result of the load. However, we still have C1 and C2, which are integration constants, and we don't know their values. So how am I going to determine C1 and C2? Here, we're going to use the boundary conditions. The elastic curve expression needs to be such that at the left support, the displacement, the vertical displacement, the deflection, is 0, and at the right support, the vertical displacement, the deflection, is also 0. If I substitute this first condition into this expression which I have obtained, this is what I'm going to get. So all of these terms cancel, and I'm left with C2. So from this first boundary condition, I already know that C2 must be equal to 0. For the second boundary condition, I'm going to do the same thing. We still don't know C1, but we already know that C2 is equal to 0, so I'm not even going to show C2 here. So then we have 2 times C1 is going to be equal to 40 minus 40 over 12 plus 40 over 6. So C1 is going to be 40 over 24, which is about 1.666 reoccurring. So now we are finally done. Alright, so previously this was the expression we had for the elastic curve. And now we know that C2 equals 0 and C1 equals 1.666 reoccurring, which is actually 5/3. So we can finally write the equation for the elastic curve, which is nu of x is equal to. So let's check to see if this equation we found is actually correct. We know that for the simply supported beam, the deflections here and here must be 0. And since this is a common problem, we also know that the deflection in the middle of the span at its maximum value is equal to. So this EY is actually here also. I have forgotten about it. This is quite common because we integrated twice and then we just kept this fraction out of the integration, and then I forgot about it, but it's actually here, the bending stiffness. So this is the actual expression. So now let's check to see if nu of 0, which means left support, is equal to 0, no deflection at the left support, no deflection at the right support, and max deflection in the middle of the span, which is L/2. So right away I'm just going to ignore this EY because it appears here again, and here it's just 0, so it doesn't make a difference. So let's first check this one out. If I substitute x with 0 here, 0, 0, 0, then I'm just going to get the deflection is 0. So this one is correct. Now the next one, substituting x for L. Again, I'm going to ignore this fraction here because it doesn't change the fact that this one inside the brackets must be 0. This is going to be 80 minus 160, 80 again. So 80 plus 80 minus 160, this is 0. So this one is also correct. So now let's check the final one. This yields 25/24 times 1/EI. So let's check to see if our expression returns the same. So nu of L/2, which is 1 meter, is equal to 25/24 times 1/EI. So our expression for the elastic curve, at least in at these three locations, left support, middle of the span, and right support, yields the correct values. So now that we have the expression for the elastic curve, which gives us the deflection at any point along the axis of the beam, we can just substitute the values and find out what the actual number, the value of the deflection is at any given point. Usually, you would want to know the maximum deflection of a beam. So in this case, because it's a simply supported beam, the maximum deflection happens at the middle of the span. So, as we have seen before, at the middle of the span, x is equal to L/2, which is equal to 1 meter. At this location, we have all we need to know now is this. What's the value of E? What's the value of I? E is the elastic modulus, the modulus of elasticity of the material. Since here we are using steel, I'm going to say that E is equal to 200 gigapascals. And I is a property of the cross-section. Our cross-section here is this one. It's an angle. And here on this website, we can see the values of the geometric properties of this cross-section. So our cross-section is 100 by 100 by 10. So it's this one, 100 by 100 by 10. So we need the second moment of area, which is I. But if you look at the table here on the left, you will see that there are three values for second moment of area. So we have here axis YYZZ, axis UU, axis VV. So what's this about? So here we have our L section. This is the shape, and he drew three axes. He drew one axis parallel to the direction of the legs, and he drew a second pair of axes, which is actually the principal axis. So it's rotated 45 degrees with respect to the legs of the L section. So we actually have three values of the second moment of area. We have the second moment of area for the rotation about this axis. We have the second moment of area for the rotation about this axis, which is 45-degree angles from the face. And we have the second moment of area for the rotation about this axis, which is perpendicular to this one. So this and this are the principal axes. So here we would have to know around which axis our beam is bending so that we can choose the appropriate value for the second moment of area. In this case, I'm going to imagine that the cross-section, our L shape, is being rotated around this axis. So for this axis, which he calls here YY or ZZ here, we have the value of the second moment of area being 177 centimeters to the fourth. So now we can finally calculate the maximum deflection which happens in the middle of this beam. So our maximum deflection is going to be equal to nu of L over 2, which is 25 over 24 times. Here I need to do some conversions, because to get to this formula here, I calculated all the values using kilonewtons and meters. Alright, so I need to use these same units here and here. E times I is equal to 200 times 10 to the 6 times 177 times 10 to the minus 8. So we get 0.0029, and since we're using meters, this is meters, or 2.94 millimeters. So this is the value of the deflection in the middle of the span of our simply supported beam with a uniform load. Alright, so we're done with the first part, which is the analytical analysis of this beam. We have found the elastic curve of the beam, and we also found out that the maximum deflection is 2.94 millimeters. That A is for analytical. So now let's do the same in ANSYS and see what kind of a result we're gonna get. In ANSYS, we're gonna do pretty much the same we did here. So I'm gonna create a line which is gonna represent the axis of the beam, and then I'm gonna create a cross section with the shape of the L, and I'm gonna associate the two. I'm gonna say this cross section should be applied to this axis. Then I'm gonna create the boundary conditions, supports on both ends, and I'm gonna apply the loads. That's basically what I'm gonna do in ANSYS, and then we're gonna see if I get the same deflection results. Alright, so here in ANSYS, this is the mechanical EPDL window. What I'm gonna do is basically follow that menu on the left. So we're gonna go step by step creating our model. First of all, I'm gonna define the kind of element I'm gonna use. I'm gonna use element beam 188. That is a simple beam element. Then I'm gonna define the material properties. This model only has one material, which is steel. So I'm gonna go to structural, linear, elastic, isotropic, and set the elastic modulus to 200 gigapascals and the Poisson's ratio to 0.3. Notice that I'm setting all values in SI, unmodified units, meaning meters, newtons, kilograms, etc. Then I'm going to define the cross section, which is the L shape. So here it is, again, 100 by 100, 10 millimeters thickness, again defined in meters. Then I'm going to go to modeling, create, and I'm going to create three key points actually, 2 key points to create a line, and then one additional orientation key point which I'm going to use later on. So first of all, I'm creating 2 key points. They are 2 meters apart because these key points are going to define the line which is the axis of our beam. So I have key point 1 at the origin, key point 2 2 meters apart in the x direction, and I also have key point number 3, which is above key point number 1. It's going to be useful later on. Now that I have the 3 key points, I'm going to use the first 2 to create a line between them. This is going to be the axis of my beam. Next, I'm going to set the attributes of this line, because for now it's only a line. We need to convert it into a bunch of elements and nodes, because finite element analysis solves models composed of elements and nodes, not composed of lines and key points. So here I have to tell ANSYS, you're going to make a mesh of nodes and elements along this line, and when you do create this mesh, these are the properties you're going to use for the elements you're going to create on top of this line. So this is the properties window, the attributes window actually. So as you can see, I'm going to be defining the material number. There's only one, so there's no alternative here. I'm going to be defining real constants. I'm actually going to skip this one because our element beam 188 doesn't have any real constants. Then I'm going to choose the element type, which is beam 188. It's a simple beam element. And then I'm going to choose the cross section, which I'm going to apply to this axis. Again, we only have one cross section defined in this model, so I have no other choice. And I'm finally going to check the box which says pick orientation key points. I'm going to check it, it's going to say yes, and then I'm going to click OK. When I click OK, ANSYS is going to wait for me to click on the orientation key points to this line. And just so I can see all the 3 key points that I have defined, I'm going to plot the key points, and I'm going to now click on the 3rd key point which I had created previously, that key point which was floating above my beam. This is an orientation key point. I'm going to show you what it does. So I click the key point, I click OK, and the final attribute I have to define here is the size of the mesh. How many elements am I going to create along this axis? So this is what I'm going to do now. I have two options. I can say how long the element is, its length, or I can say into how many parts should ANSYS divide the line. I'm going to say that ANSYS should divide the line in 100 parts. So I'm going to click OK. And there you go. ANSYS is now displaying to me the line with 100 divisions, as I have requested. But ANSYS has not yet created the elements along this line. Indeed, if I try to plot elements, you're going to see this error message. It says, I can't plot elements. There are no elements. Why are there no elements? Because I have only told ANSYS, when you do make the mesh, this is how the mesh is going to look. 100 divisions, this kind of element, this kind of material, etc. So I haven't yet created the mesh on this line. So this is my next step. There you go. Now I can plot the elements, and what you're seeing here are the actual elements, but you can tell them apart from the line itself. They're both just a single blue line, so how do you know you even created the elements? You can plot elements and it's not going to display an error message, but you can't see them. It would be best if you could see the elements you have created. So this is what we're going to do now. We're going to go to plot controls, and we're going to ask ANSYS to display the cross-section of the elements we have created. So we activated this box which says display of element. Click on it and it goes on, and there you go. ANSYS is now showing the cross-section plotted on top of the axis we had before. So as you can see, there's the L shape, and you can also see the element divisions, both in the longitudinal direction, which is the 100 elements we requested, but you can also see the mesh in the other direction, the mesh in the cross-section itself. So finally, we're going to apply the boundary conditions. I'm going to plot the lines again, and the first thing we're going to do is apply the supports. There's no particular reason for this order. I just chose to begin with the supports. You could begin with the loads or anything else, but I'm going to apply supports first. So I'm going to support both ends of our beam, and at each end I have one key point. So I'm going to apply supports to the left key point and to the right key point. So first of all, I click on the left key point, which is at the origin, and here I tell ANSYS which directions, which degrees of freedom I'm going to restrain. So since my load is going to be a vertical load in the Y direction, I want my supports to prevent Y movement. So UY, displacement in the Y direction, is a degree of freedom that I have to constrain. That's the clearest one. But I should also constrain UX, at least for this one. Because if I don't constrain UX on either of the key points, my beam can just move freely on the longitudinal direction. And this is going to cause problems during the solution. So I'm just going to restrain movement in the X direction for this single key point. And for the same reason, I'm also going to restrict movement in the Z direction. We are actually not interested at all in what happens in the Z direction. All our movement, our deformation, should happen in the XY plane. So any movement in the Z direction, I'm going to block. And I'm also going to have to block rotations about the X-axis. The X-axis is the beam's axis itself. So a rotation about the X-axis is this kind of rotation. We're also not interested in this kind of rotation. So I'm going to block this rotation on the left support, so that ANSYS doesn't make my beam spin infinitely without restriction. Now I'm going to define constraints for the right support. And from the right support, I'm going to remove UX because I want one of the supports to be able to move in the longitudinal direction. Because when a beam bends, the extremities move closer to each other. So if I keep this extremity fixed, I have to let this one free so it can move in this direction and approach the other one as the beam bends. If I didn't do this, then the tips of the beam would try to approach each other, but the supports would keep them apart. So I would be, in effect, tensioning the beam with this boundary condition. So I have set the supports for the both key points at the extremities of the beam. These are the supports you were seeing in my slide, the true triangles we usually draw when we are representing structural analysis models. But like I said, I do not want any sort of movement in the Z direction or any sort of rotation about the X-axis. So I'm going to prevent every single node of this model from moving in the Z direction or rotating about the X direction. So here I'm going to plot all the nodes, and I'm going to set constraints to the nodes. So earlier we set constraints to the key points. Our model only has 3 key points, one at each end of the beam and one floating above for orientation. But our model has a bunch of nodes. Each element has 2 nodes, and we have 100 elements. So we have 101 nodes. But we also have orientation nodes above our elements that show what is the direction of the cross-section. So is the cross-section like this, or is the cross-section like this? How is it rotated with respect to the axis that passes through here? That's what the orientation key point is for. So I'm going to select all the nodes of my model, and I'm going to set displacement constraints on them. So I'm going to select all the nodes that belong to elements. The nodes floating above do not matter. And I'm going to set constraints on all these nodes. I'm going to set the following constraints. They're not going to be able to move in the z direction or rotate about the x direction. Now I'm going to go forward and apply the loads to this beam. ANSYS offers many alternatives with regards to how to apply loads. And I'm going to choose the following method. I'm going to apply distributed loads to the elements themselves. So we have 100 elements. I'm going to apply loads to each one of them. Instead of selecting each one of the 100 elements by clicking on them, I'm going to click Pick All in the selection window. So this new window pops up. This is the window I need to fill to introduce the loads in my model. But right at the beginning, ANSYS is asking me for a value which I'm not familiar with. I mean, here I expected only to give ANSYS the value of the load. So I was only expecting to have to type somewhere in some box the number 5,000, which is our load, 5,000 newtons per meter. But ANSYS is asking me for a load key. So what is a load key? Whenever you run into this kind of an issue in ANSYS, the best thing to do is to check the help. So I type on the command line help, 188. 188 is the number of the element I'm using, beam 188. In beam 188's help page, I hope to be able to learn what these load keys are and how they are applied to this element in particular. So here we have a representation of a generic beam 188 element. As you can see, the element has three nodes, I and j, which define the axis of the element, and the node k, which is the orientation node. The orientation node floats above the axis of our beam, and its function is determining the direction of the cross section. Is it rotated like this? Is it rotated like that? And if you were to read this help page, you would see that those numbers inside circles are actually the load keys. So as you can see, this element, beam 188, has 5 load keys, 1, 2, 3, 4, 5. And each load key is applied in a different direction or at a different point. Load keys 1, 2, and 3 are for loads that are applied along the length of the element. And load keys 4 and 5 are for loads that are applied at the ends of the element. We wish to apply our load along the length of the beam. So we're going to have to use load key 1, 2, or 3. How do we choose? We choose based on the direction. Right away, load key number 3 runs along the axis of our beam from node I to node j. So this is not what we want. We want a load that is transversal, that is perpendicular to the axial direction. So we are either going to use load key 1 or load key 2. And to be able to determine which load key we're going to use, we're going to have to look at the elements we have created in our model and see where the y and z local axes are. Here we're going to be looking at local element axis, not at the global axis. The global axis appear at the beginning of the model near key point 1, and you see the triad, XYZ, actually, right hand rule, XYZ. But each element has its own local axis. So if you go to plot controls and symbols, you can ask ANSYS to plot the axis for each of the elements. And as you can see here, ANSYS has drawn on top of the model the X, Y, and Z axis, local axis for each element. So I'm going to zoom to the beginning of the beam so we can simultaneously look at two things. Local axis for a few of the elements and the global XYZ axis. This is what you're seeing here. So as you can see, ANSYS uses white for X-axis, green or yellow, I don't know, for Y-axis, and blue for z-axis. That's the color scheme. So the global triad is indicated there, XYZ. The other axis, those thinner, smaller axes that are appearing at the centroid of each element, are the local axis of that element. And the color schemes also apply here. So as you can see, the white line indicating the local x-axis runs along the length of our beam. So as we saw on the help page, the x local axis is the longitudinal axis. Now the y-axis in green, I'm just going to call it green, and the z-axis in blue can also be seen in this image. So perhaps this might seem strange, but the local z-axis is pointing towards the y global axis, and the local y-axis is pointing towards the negative global z-axis. There isn't necessarily any correspondence between global axis and local axis. You can choose the direction of local axis as you wish. And indeed, this is what we did. We chose the direction of the local z-axis when we chose the orientation key points. So we had our beam right here, and we defined an orientation key point up here. What ANSYS does is the following. ANSYS knows where the centroid of the element is, and ANSYS also knows what is the longitudinal direction of this element, because the element has two nodes. So it points in this direction. Then what ANSYS is going to do is point the z-axis, the local z-axis, towards the orientation key point you have chosen. And that's the result you see there on the screen. Our local z-axis points towards our global y-axis. And this is the direction along which we want to apply the loads. So our loading should be in the direction of the negative z local axis. And if we go back to the help once again, we're going to see that the load key that matches the negative z direction is load key number 1. So now we know to which load key we're going to apply our loads. So we go back to applying pressures on beams. I'm going to turn off display of the local axis because they kind of get in the way. And I'm going to go back to defining pressures on beams. Now we know that load key is number 1. And now we can set the pressure, which is 5,000. Notice also that this 5,000 should be positive because the load should be pointing downwards along negative y. And our z-axis points upwards towards positive y. But our load key points towards the negative local z-axis. So a positive load key applies a load against the local z-axis. And that's what we want. And then I click OK. And as you can see, we have the distributed load being displayed on the screen. Sometimes you change the view and it may disappear, and you can just replot and you're going to see it again. I'm going to go back to the simple line display without display of cross sections so that we can see more clearly our boundary conditions. So now we're done pre-processing our model. We can move on to solution. So we enter the solution step. Here we're going to do very little. We're going to choose the analysis type, which is static, and then we're going to solve the model. Nothing else needs to be done here. And then we move on to post-processing. So the first thing we're going to do here in post-processing is read a result set. In this case, we only have a single result set, so we're going to read it anyway. And now let's look at some results. We were interested in deflection, so let's plot the deformed shape, like so. Now let's improve on this plot a bit by also showing the original position of the beam. Now you can see the original position in white and the deflection in blue. We can also plot in colors, for example, the deflection along the y direction. So now ANSYS colors the results based on the value of the UI degree of freedom. That's the color plot you're seeing. Again, the white line is the original position. So as you can see, the maximum value of the y displacement is minus 0.02946. First of all, why is it negative? It's negative because it's in the negative y direction. Y is positive, going up, but our beam is going down, so it's negative deflection. And since we're using SI units, this value is in meters. So 0.002946 is actually 2.946 millimeters, which, if you remembered, is the same value we found before. But let's now plot the deformed shape with the display of the cross-section, as we did before for the elements. So there you go. Now you can see a representation of the 3D model. The cross-section has been extruded along the axial line, and it's been shown in its deformed state. And the value doesn't change, of course, it's still the same model. This is only a display trick to show the 3D model. And now I'm going to create a quick animation. In this case, the animation isn't quite so useful. Sometimes it has useful information, but in this case, it's way too simple. So you're just going to see our beam oscillating up and down. Again, the colors in the UI displacement. And now I'm going to go back to displaying the elements as lines for one last plot. So when we simulate something in an advanced software such as ANSYS, we may expect some special results, but what we should actually be looking for is familiar display of results. So when we perform hand calculations, for instance, we often draw the deformed shape as a diagram beneath the beam, right? So I'm going to generate the same plot in ANSYS so we can visually check to see our result in a more conventional way, in a way we are accustomed to. So for that, I'm going to have to create what is called an element table. I'm going to create an element table which maps the value of UI, meaning the vertical displacement. So when I plot this element table, it's not going to look anything special. It looks exactly as it did when earlier I plotted the vertical displacements at each node. So this is basically the same thing, almost the same thing. But the advantage here is that when I create an element table, meaning I have mapped some result to every single element in this model, I can use a different plot option which ANSYS also offers, which is the line element results. So I'm going to plot the UI elements table, which I have just created. I'm going to plot it on the undeformed shape. And there you go. ANSYS drew a diagram which shows colored bars indicating the value of that element table, which in this case is the UI displacement, at every single element. So this diagram is basically my deflection, a diagram of my deflection. It's pointing upwards, so I'm going to invert the scale factor so that it points downwards. This is just a cosmetic change. And there we have it. Now we have already seen that the maximum displacement, 2.94 millimeters, matches the one we obtained before in the analytical solution. But I'm also going to want to look at the shape of the elastic curve. Does this elastic curve, which we obtained in ANSYS, match the one we calculated analytically? So this is what I'm going to check now. There are many ways of doing this. I could extract the vertical displacement for each node along the element, calculate the corresponding displacement using my elastic curve, which I obtain analytically, compare those values, see if they match, or perhaps I could have exported from ANSYS this shape in the form of a graph. There are many ways. The one I'm going to use here is perhaps a bit ridiculous, but it's also visual. And that's why I'm choosing it here. So this is what I'm going to do. I'm going to capture this image that's plotted here in ANSYS, and I'm going to implement the analytical elastic curve I have calculated in Excel. So this is what you're seeing here. So I copied to Excel the expression we found for the elastic curve. I have defined the input parameters for this expression like EI, Q, and L. And I have calculated the value of nu of x, meaning the deflection, at 20 points along the length of our beam. That's what those two columns x and v mean. And then I plotted x against v, meaning the position along the axis against the deflection at every point. So this curve in blue, which you see in Excel, is a representation of the analytical elastic curve we obtained. Now I'm also going to capture an image of this elastic curve, and I'm going to go on with my ridiculous approach. I'm going to open an image editing software, and I'm going to superimpose those two images. I'm going to set one of them to be a little bit transparent. I'm going to put the other one on top of it, and then I'm going to stretch and scale both of them so that the ends of the beams match between the two images, and so that the maximum displacement matches between the two beams also, because we already know that the maximum displacement is correct, 2.94. Those two match. So I'm going to stretch the image horizontally to make the length match, and I'm going to stretch the image vertically to make the maximum displacement match. And here you can see the result. When I make the beams match horizontally and at the maximum point, the curve itself, meaning every point along the analytical elastic curve, matches one of the colored ANSYS bars. So obviously I can't be too precise with this comparison. I'm just making a visual comparison, but at least I can show you that the results mostly match. If there was any difference in the shape of these curves, this difference would be apparent here in the superposition, or this difference is way too small that I can't even detect it when I make the length and the height match. So that's the final demonstration of how our analytical results match the results we obtained in ANSYS, both in terms of maximum value and in terms of the shape of the elastic curve. Okay, so we created the model using ANSYS APDL, and it was a lot of work, right? Clicking on key points, selecting key points, creating lines, creating sections, all that is a lot of work. And if we wanted to change anything, let's say the length of the beam, we would basically have to start again from the beginning, erasing key points and all of that. So this is quite a slow process, and there's a way to speed it up. Every single command that we did by clicking on buttons on the screen has been recorded in the session editor. So they're listed as text commands, and if you copy these text commands into ANSYS and paste them into the command line, it's going to repeat those commands and it's going to create the model for you. So let's invest a bit in APDL. Let's learn how to create a model like this one, which is a very simple model in ANSYS, using APDL by typing directly the commands in the APDL language. So here we are, back again in ANSYS Mechanical APDL. I have split the screen. On the left is ANSYS. On the right is the IDE I use for editing APDL code. So on the first command, I'm going to enter the preprocessor, that /prep7 does this. It's the same as clicking preprocessor. And then I'm going to start by attributes, just like we did using the graphical user interface. So here I'm defining the element as being 188, and then I'm defining the material properties. So the ET command defines the element type, the MP command defines the material properties, and I'm setting just the elastic modulus and Poisson's coefficient. And then I'm going to go on to the sections. In this case, it's a single section, our angle section, and the commands are secType and secData. So the first command, secType, is going to create a section, and it's going to inform ANSYS of what's this section like, meaning it's a beam section, it's an L shape. And the following command, secData, which has to be issued immediately after secType, is going to inform ANSYS what are the dimensions of this section, which is an L section. So it's going to interpret the information in secData in the context defined by secType. So in this case, point 1 and point 1 are the dimensions of the sides of our angle, and point 01 is the thickness of each of the legs of the angle. And as you can see, once we have issued the command in APDL and pasted on the command line, the graphical user interface shows the results of those commands. So the materials have been defined, the element type has been defined, the cross-section has been created. And now we move on to the next phase, which is the solid model. So as you may recall, we were creating 3 key points. Key point 1 and 2 for the axis of the line, key point 3 above as an orientation key point. The command for creating key points is K. So here you see me issuing this command k 3 times. Each time I'm creating a different key point. The first argument, 1, 2, and 3, is the number of the key point, and the next arguments are the x, y, and z coordinates of the key point. Next, I'm going to create the line between key points 1 and 2. It's the command L. So my solid model is done. I have 3 key points and 1 line. So next we're going to create the mesh. Now if you recall, what we first did was set the attributes of the mesh, then the size of the mesh, and then we created the mesh. So here we're going to do the same. First of all, setting attributes with the command lat, L attributes, line attributes. So there I'm going to say that I'm using element type 1, that I'm using material number 1, and cross-section number 1. I also have to inform, using the lat command, that I'm using key point number 3 as the orientation key point. So that's the 3 you see there in the lat command. Next, I'm going to issue the lesize command to divide the line in 100 elements, and then I'm going to create the mesh with the lmesh command. Then I'm going to display the elements using the 3D shape by turning on the cross-section display. So this is done using the /eshape command, and then I use the eplot, which plots elements, to show the elements in their 3D shape on the screen. So now that the mesh has been created, I'm going to move on to the boundary conditions. If you recall, we applied boundary conditions to both key points of the axis of our line, and also to the nodes of each element we created. So first of all, I'm going to apply the boundary conditions to the key points. To the first key point, which is at the origin, it's key point number 1, I'm going to apply 3 displacement constraints, ux, ui, and uz. It doesn't move in any direction. 1 rotation constraint, which is rot x, which prevents the beam from twisting around. This is done using command dk, which sets displacement for key points. I'm going to issue the command again with argument number 2, meaning key point number 2, and I'm going to constrain only displacements ui and uz. So now I have generated supports for both extremities of the beam. Now I'm going to create supports on all nodes of the beam. This is done not using command dk, which is for key points, but command d, which is for nodes. So I'm going to apply restrictions in the uz and in the rot x, rotation x direction using the d command, as you can see there. So this concludes our supports. We have created supports to guarantee movement only in the xy plane for this model. Next, we're going to apply the loads using command sfbeam. As you recall, this was the command that required us to take a look at the help to learn what a load key was. And here we're going to have to use this load key information again. So we issue the command sfbeam to apply distributed pressure on all elements. And the fields you have to fill with arguments are all, meaning I'm going to apply pressure to all elements, 1, that's the number of the load key, press, meaning I'm applying a structural pressure, and 5,000, which is the value of the load I'm applying, 5,000 newtons per meter. Now my boundary conditions have been defined. So I have the geometry, I have the materials, I have all the other attributes, I have the boundary conditions. I can finally solve the model. So I enter the solution processor using the /solu command, and I initiate a solution by typing ntype, 0. This initiates a static analysis, and I issue the command solve to solve the model, quite simply. So the model has been solved, and now we go to post-process. General post-process is processor /post1. So the first thing we're going to do, like last time, is going to be read the first result set. Again, we only have one result set in this case, so reading the first one or the last one would give us the same result. So now we have read the first result. Let's plot the deformed shape. This is done using the pldisp command. The pldisp command plots the displaced form of our structure. If we want to see the structure with the representation of the cross-section, we have to turn it on using the /eshape command. So there it is. And now I'm going to plot the displacement, but in colors I'm going to show the UI degree of freedom. So I'm going to plot y direction displacements in colors. That is done using the plnsol, plot nodal solution command. So I'm going to plot the nodal solution for u, the displacements, along y, the y direction. That's what this command does. And finally, the last thing we did last time, I'm going to do here also, was create an element table and map the UI values to this element table, and then plot our deflection diagram. This is done by first creating the elements table with the etable command, as you can see, and next by plotting the diagram using the pls, plot linear element results command. The final argument on pls is the scale factor, which makes the graph larger or smaller, and you can even invert our plot using -1 or +1, and we're done. We have created the same model as before, but with just about 60 lines of code. So here I'm going to comment the code a little bit just to make clear what each line does. and our code is done. I can just copy this code, paste it on the command line, and it's going to work. It's going to generate the model, solve the model, plot the results. So this is already a little better, a little faster than clicking on every command on the graphical user interface. But we can improve it even more. First of all, we have used some hard-coded values, like the dimensions of our beam. We chose the width of 0.1 and the thickness of 0.01. Instead of using those values inside the secData command, I'm going to use parameters inside the secData command, and I'm going to set these parameters at the beginning of the code. So width is going to be equal to 0.1, thickness is going to be equal to 0.01. This equal operator is assignment operator. So it's assigning to the word width, the variable width, the value of 0.1. Then I can use this variable throughout my code. So I'm going to do the same with the length. The length was being used in the key point definition, and I'm going to do the same with the value of the load. So I have 4 parameters: width, thickness, length, and Q. These 4 parameters are defined in the beginning of the code and used by the ANSYS commands that follow below. So if I copy all the commands, paste them on the command line, ANSYS will solve the model for me. If I want a new model with different geometry, let's say I want to change the length from 2 meters to 1 meter, I just change the parameter length at the top, I erase the model, I copy the code, I paste the code again, and voila, my model is now only 1 meter long. My beam is 1 meter long. And just like this, we can parameterize any other quantity, anything else we want in APDL. This is a very simple code. All I did was to make parametric the geometry and the loads. So this already is a much better version of the code, because it's easy to adapt, it's easy to make a new model, it's easy to make some tests. Our simulation matched our analytical results for a beam of 2 meters in length. But what if the beam was 4 meters in length, or 10 meters in length, or half a meter in length? Would it still match the analytical results? Hard to say. We hope so, but we don't actually know. We would have to run the analysis to be able to tell. So having the code here in text format with parameters, with variables storing values, is a great way to be able to quickly run a different simulation, a slightly different simulation. So this was our next level of development in this problem. We began with the analytical analysis, then we used ANSYS graphical user interface mode, then we used ANSYS in APDL mode, and we parameterized the APDL code to be able to quickly change our geometry.